Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD Homogeneous Fluid Mixing through a special type of heat exchanger using SolidWorks flow simulation. This is a special type of homogeneous fluid mixing, and in this case we can have the temperature at the exit location as per our requirement. The advantage of this type of fluid mixing is that we can have better control of temperature. Whatever we like, we can get the temperature at the exit location. We are having two inlets. This is one inlet for hot water, and from this one we will be providing cold water, and these two will be mixed at this location, and finally at the exit location we will be getting homogeneous fluid mixture at a specific temperature as per our requirement. Right? For understanding the geometry, let us cut this model from specific plane. Let us cut this model from front plane. We can understand this one better way. So this is the opening. From here we will be providing water at 90 degrees centigrade, and from this opening we will be providing water at a lower temperature, but mass flow rate of that one will be very high, or we can say velocity of this one will be very high, as it will be passing from these small openings, and at this location homogeneous fluid mixing will be occurring at this location, and finally at the exit location the homogeneous fluid mixture at a reduced temperature, and the temperature at the exit location can be controlled very easily by controlling the mass flow rate or the velocity of water at the inlet location. In this case we are considering that velocity of hot water will be fixed, and to get the reduced amount of temperature at the exit location we can vary the velocity of water at the cold location. Right? The lists have already been provided and the geometry has been checked, so it is perfect. Now flow simulation environment will be created with the initiation of wizard, and we are keeping the name of the project as project 7. Next to that, but to select the unit systems, we are considering unit system as SI, and the unit of pressure will be Pascal, and we are keeping temperature unit to be degrees Celsius as usual. Next to that, we are to consider internal fluid flow analysis, and definitely heat conduction in solids will be there. By the same time we will be considering gravity, and the direction of gravity will be Y, as indicated by the green arrow at this location, lower left corner. So gravity along Y direction will be minus 9.81 meter per second square, and along Z it will be 0. Next to that, we have to select the fluid, and we are considering single fluid. It will be water. We will be considering water at different temperatures, and that will be mixed in this special type of heat exchanger. So default fluid we are considering as water. Next to that, we have to consider the material for the container. Let us consider this copper. Next to that, we are considering default outer wall thermal conditions and default roughness. Next to that, atmospheric pressure will be 101.325 Pascal, and temperature will be 20 degrees centigrade. At the same time, the solid parameters, it will be having temperature also 20 degrees centigrade. Let us finish this. This is the computational domain. We can hide this domain. Here in this heat exchanger we are mixing water at different temperatures, so it will be having single fluid domain, and material has also been provided, so we have to apply boundary conditions. And for providing boundary conditions, it is always suggested to have a segmented view of this model. So we'll cut this model from a specific plane. Let us cut it from front plane, and let us apply boundary conditions. So inside boundary conditions we can provide mass flow rate also. Better to consider inlet velocity. Water will be passing from this opening at a velocity of 0.1 meter per second, and thermodynamic parameters 90 degrees centigrade. Next to that, I'm going to apply cold water at this opening, and that will be passing at a different rate also. So inside boundary conditions, it will be inlet velocity from this opening, and initially we'll keep this velocity as 1 meter per second, and the temperature will be 10 degrees centigrade. So Two boundary conditions have been applied. Next to that, we have to apply another one, that means atmospheric pressure at the exit location. For that, we have to cut this model from different plane again. Let us cut it from top plane. Selected that location, and it will be atmospheric pressure or environmental pressure at the exit location. Green check. All the boundary conditions have been applied properly. Next, we have to select some goals. We can have a lot of goals, but our main aim should be to have the temperature at the exit location, and in optimization we want to have desired amount of heat at the exit location. Initially, we'll see the temperature, pressure, velocity, etc. at this exit location as goals. This will be surface goals definitely. So insert surface goals, and we want to select temperature, pressure, and velocity at the exit location. Let's find average temperature of fluid, average pressure, and average velocity also at the exit location. Great check. So we have selected 3 different goals, and main aim is to find the temperature at the exit location, and that to be controlled using velocity of water at the cold location, right? Next, we have to run this simulation, and for viewing the dynamics of these flow particles, let us make this model completely transparent. We made the model completely transparent for viewing the dynamics of flow particles. Okay, right. Next to that, we should run it. Let us run this with new calculations. Iterations have already started. Let us view the goals from the solver window itself. You can see clearly that how fluid is entering from this location and it is being mixed at this location. We can cut this one from different plane also. We will be viewing this fluid mixing through different planes, right? You'll see this one from top plane also. Survey is finished. We can see the results from here again. All the results are converged. You can see that temperature at the exit location is 65.82 degrees centigrade, and average total pressure is 101,409 Pascal, and average velocity at the exit location is 0.4088 meter per second. Right. Next to that, we'll see our results from the different cut plots and also surface plots also. Results, cut plots, insert cut plots, and we're going to see temperature of fluid from front plane. Temperature of fluid from front plane, we'll see. We can see the temperature at the hot inlet is 90 degrees centigrade and at the cold inlet is 10 degrees centigrade, and is being mixed at this location. And finally, at the exit location, its temperature is in the range of 63 to 72 degrees centigrade, right? Which is indicated by yellow color. Let us see this cut plot in the form of animation. Let us clear ahead these things. We want to see surface plots. Insert surface plots, and we see surface through all the surfaces. And we will see temperature of fluid. We will check. You can view temperature of fluid at the different surfaces. Let us rotate this and see clearly. At the inlet of hot opening, temperature is 90 degrees centigrade, and at the entry of cold opening, it is 10 degrees centigrade. And at the junction where fluid mixing is going on, at this location, temperature is in the range of 27 to 45 degrees centigrade. it is, and at the exit location temperature is in the range of 63 to 72 degrees centigrade. Okay. Next to that, we have to see dynamics of flow particles through this heat exchanger. So we have to clear and hide these surface plots. And we want to see dynamics of flow particles from here. So flow trajectories, insert flow trajectories. When you see temperature of fluid, let us consider numbers of flow particles to be 200 numbers. Select other. It will be lead number 1, and from here also we can select other. It will be lead number 2, and from this opening also select other. It will be lead number 3. Now I'm gonna hit crane check. We can see the dynamics of flow particles in the form of animation. Let us play these things. Flow trajectories, let us play. It is clearly visible that from the hot entry water is entering at 0.1 meter per second and its temperature is 90 degrees centigrade, and at the cold entry temperature of water is 10 degrees centigrade, and which is passing at a high velocity of 1 meter per second. And finally at the exit location, after homogeneous fluid mixing, we are getting the temperature as in the range of 63 to 72 degrees centigrade, which is indicated by yellow color. Right? Next we will go for some kind of parametric study, and we'll see at different velocities of cold water what will be the temperature ranges at the exit locations. Right? So we'll close this one. Flow trajectories, clear and hide, and we'll go for parametric study. Solve new parametric study, and we're going to go for design of experiments and optimization. And in this case, we have to depend on input variables, and we are considering input variables to be cold water flow rate, right? So it will be obtained from simulation parameters, and it will be obtained from generally boundary conditions. It will be inlet velocity of cold water we're considering velocity normal to the face as the input variable. Each value was decided 1 meter per second. We'll vary this one from 0.5 to 5 meter per second, right? Let us change this from 0.5 meter per second to 5 meter per second. Let us see the output parameters, and we're considering all the goals to be optimized. Let us see the scenarios. Let us create that parametric study. We have created parametric studies at different velocities of cold water. We can vary these velocities. Let us consider these velocities to be from 5 to 1 in the reverse order. Initially it will be 5 meter per second. Next one will be 4 meter per second. This one will be 3 meter per second. This one will keep it to 2 meter per second. And 1 meter per second is already considered. So with these 5 different set of input variables, we have to find out our goals, right? So let us run it. Iterations are over. You can see our result right now that at different velocities of cold water, we're getting different temperatures at the exit locations. When the velocity at the cold water is 5 meter per second, the final temperature at the exit location is 35.04 degrees centigrade. And when the velocity of cold water is 4 meter per second, then temperature at the exit location is 39.04 degrees centigrade, and when the cold water velocity is 3 meters per second, the temperature at the exit location is 44.6 degrees centigrade. And in the fourth experiment, when the velocity of cold water is 2 meters per second, the temperature at the exit location is 52.84 degrees centigrade, and at 0.5 meter per second velocity at the cold location, temperature at the exit location is very high. It is 75.27 degrees centigrade. It is clearly evident from the set of experiments that when the velocity of cold water is increasing, temperature at the exit location is also decreasing, right? Now from this set of results, we can have an idea that at what velocity we can have what results. Suppose you have to get temperature at the exit location to be 50 degrees centigrade. So we can assume that to have temperature at the exit location to be 50 degrees centigrade, we have to set the velocity of cold water to be in the range of 2 to 3 meters per second. Let us do that analysis again. That is, finally we want to get the water at the exit location to be 50 degrees centigrade. For that, we have to set some specific velocity for the cold water. Let us go for a new analysis, and our aim is to finalize the temperature at the exit location to be 50 degrees centigrade. For that, start a new parametric study, and we want to go for goal optimization. And in this case also same thing, the input variable will be cold water velocity that we obtain from boundary conditions. It will be velocity normal to phase working as a input variable, and we are considering the velocity of cold water to be in the range of 2 to 2.5 meters per second. Let us specify the range from 2 meters per second to 2.5 meters per second. We'll check, and we have to select the goals definitely. To select only one goal, that means we have to have temperature of the exit location to be 50 degrees centigrade. So we have to select only one goal. Average temperature fluid at the exit location we're considering as the main goal. Target value is 50 degrees centigrade, and we want to achieve this target with a variation of plus minus 0.1 degrees centigrade. We'll check. Let us see the scenario. We're having total 128 numbers of iterations maximum. Initially, we will start iterations with the maximum one. Then in the next case, we will start with the minimum one. In this way, it will try to minimize the gap in between and try to optimize. Right? Let us run this. You can see here the solution is converged. So within 4 set of iterations, we got the results. And you can see that when the velocity of cold water is 2.5 meters per second, then temperature at the exit location is 48.26 degrees centigrade, and at the design point 2, when velocity of cold water is 2 meters per second, then temperature at the exit location is 52.84 degrees centigrade, and at design point 3, when the velocity of cold water is 2.3099 meters per second, then temperature at the exit location is 49.83 degrees centigrade, and at the design point 4, when the velocity of cold water is 2.29 meters per second, then got the final temperature at the exit location is 49.98 degrees centigrade. So we achieved our target with a variation of 0.01 degrees centigrade, right? So this is a very simple analysis. With this analysis, we can have any desired temperature at the exit location by controlling the mass flow rate of water, or you can say the velocity of water, right? So with this one, we'll conclude our today's analysis of homogeneous fluid mixing using special type of heat exchanger using SolidWorks flow simulation. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.